A solid right circular cylinder has a radius of r centimetres and a height of h centimetres. The total surface area of the cylinder is 800 centimetres squared. I need to show the volume of the cylinder is given by V equals 400R minus pi r cubed. So I've got a cylinder with radius r and height h. So the volume of this cylinder would be given by the area of the cross section, which is the circle, so pi r squared, multiplied by the height. Now, just comparing what I've just written there to what I need to show, we can see that we've got an r involved, but I've got a h here, and there's no h here. So I need to replace that h somehow. We were told in the question that the surface area of the cylinder was 800 centimetres squared. So if I can get an expression for the surface area, I can make it equal to the 800 and then hopefully rearrange. So for the surface area, we've got the circle on the top, which has got an area of pi r squared. And then we would have the same circle on the bottom. So we're actually going to have a surface area of 2 pi r squared, plus we've got the rectangle that wraps around that. That rectangle would look like this, where this is the height of the cylinder, h, and this length here is the length that wraps around the circle at the top there, which is basically the circumference of the circle, which is 2 pi r. So therefore the area of that rectangle is base times height, so 2 pi r times h. This is my expression for the surface area. So I can now make that equal to 800, because I was told the surface area was equal to 800. I notice at this stage that I could divide through by 2 here. And I'm now going to rearrange to make h the subject. So I would get pi r h is equal to 400 minus pi r squared. And we'll divide both sides by pi r. To find that my h is equal to 400 minus pi r squared divided by pi r. And so I can now substitute this in instead of my h over here, instead of the h that I had there. So we'll get pi r squared multiplied by the 400 minus pi r squared over pi r. I can see that when I times through by pi and then I divide by pi, they are going to cancel out. And similarly, when I times by the r squared and then divide by the r, they're going to cancel out. So actually all I need to do is just do the r times 400 minus pi r squared, which gives 400r minus pi r cubed. And that's what we needed to show. We're told that r varies, the radius of this cylinder changes. And part B says to use calculus to find the maximum value of V to the nearest centimetres cubed. So I know that a maximum value occurs when the derivative equals 0. So therefore either for a maximum or a minimum, dV by dr is equal to 0. So I'm going to take my expression for the volume that I found in part A, and I'm going to differentiate that with respect to r. So 400r differentiated will just be 400. And the pi r cubed will differentiate to be 3 pi r squared. And at a maximum, this equals 0. I can now rearrange this and solve it to find out what r is when I have a maximum. So divide both sides by 3 pi and I find r squared. And if I square root both sides, then I find that when r is equal to the square root of 400 over 3 pi, that is roughly 6.5. So when the radius of this cylinder is 6.5 centimetres, its volume will be at a maximum, the biggest it can be. The question actually wants me to find the volume though, so not the radius. I want to know the volume when the radius is the square root of 400 over 3 pi. So let's take that and substitute it back into the original expression, the 400r minus pi r cubed. And when we do that, we find that the maximum volume to the nearest centimetre cubed is 1,737 centimetres cubed. That's the maximum volume when the radius is 6.5. Part C says to justify that the value of V we have just found is a maximum rather than a minimum. So I know at a maximum, the second derivative is going to be negative. So that's what I need to show. So first of all, let's get an expression for the second derivative by taking my first derivative and differentiating it again. So when I differentiate the 400, that will just be 0 because it's a constant and doesn't change. And when I differentiate the minus 3 pi r squared, I'm going to get minus 6 pi r. So this is my expression for the second derivative. And I can say that when r is the 6.5, what we found before, the square root of 400 over 3 pi, substituting that in here, we can clearly see that we get a negative value. So when r equals 6.5, d2v by dr squared is negative. Therefore, this shows that v is a maximum rather than a minimum. If it was positive, it would have been a minimum. But it's not, it's negative. So it's a maximum.